Okay, thank you very much. Of course, I would like to join the previous speakers in thanking the organizers for their perfect conference and for inviting me to participate in this program, which up to now at least has been very exciting. So I'm in Laboratoire Casser-Brossel, UPMC, Collège de France, and INS, and I'm also at APS as the Physical Review X, as one of the two Physical Review X lead editors. So what I would like to discuss today is two quantum games that we have recently played with Rydberg atoms. The first is the implementation of a quantum Zeno dynamics in a non-trivial, large-dimensional Hilbert space. And this is an interesting and funny quantum game that leads to the generation of a new kind of Schrödinger cat states for large spin. We already heard of QZD, I should mention, in the talk of Jakob Reichel, I think it was on Tuesday morning. The second experiment is also about Schrödinger cats in Rydberg atoms. It's perhaps more useful than the one of the generation of QZD because it leads to an interesting quantum-enabled electrometer for electric fields which achieves a precision that could be of interest, in particular for mesoscopic experiments. And these two papers have recently appeared. So we play these two games on a quantum scene, on a large quantum scene, that is the nth manifold of an atom. We use rubidium for laser convenience, but to make things simpler, we consider rubidium as being just hydrogen, forgetting about quantum defects, forgetting about fine structure that brings some difficulties that are purely technical. So if we put the N2 level, I also forget about the spin, the N2 level of the nth manifold inside a static electric field, we obtain the Stark level of the hydrogen atom. We all know that's basic. They are sorted out by their magnetic quantum number, which remains a good quantum number in the cylindrical symmetry. The tip of this triangular organization there is the circular state that has only a second-order Stark effect, which I neglect here, and which has very remarkable properties that we have used ad nauseam in our cavity QED experiments. And then you have N2 of these levels, and all of them are equally spaced, separated by a frequency, the Stark frequency, that is proportional to the principal quantum number, to the electric field, and to give a rough order of magnitude, is of the order of 100 megahertz in a 1 volt per centimeter field in a typical 50 manifold. So we have a large scene here, 2,500 level, such large a scene that we feared getting lost on it. It's as large as this scene here. So we'll confine ourselves to a smaller territory, and we will isolate in this manifold of state a ladder of level that is equivalent to a spin. How can we do that? We start from the circular state here, or alternatively from a low M state that can be reached by laser excitation, and we drive the current evolution of the atoms with a resonant radio frequency field at a few hundred megahertz, whose polarization is very purely sigma plus. In those conditions, the only allowed transitions are the ones between the lower state for each M value that form here a ladder of equidistant states, 51 equidistant states. And those states turns out to be connected by dipole matrix elements that are precisely those of a large J spin, a J25, because we have 51 levels. So we can isolate in this vast scene a single ladder of level. It's much simpler, but of course it's already a Hilbert space with dimension 51, so it's already something interesting to play with. All these experiments are performed in a very simple experimental setup. We just have two plates to apply the electric field, an atomic beam, thermal velocity, no cold atoms, lasers to excite the low M laser excited levels in this ladder, in this spin ladder. And we all around the capacitor plates here, we have ring electrodes that are used to generate a very pure sigma plus polarized RF field in the middle. This is fairly simple now using four channels programmable synthesizer, and thanks to a painstaking optimization of the voltages and phases applied on these electrodes, we can reach a polarization precision purity better than 99%. And finally, the atoms are read out by field ionization. Of course, this is a large spin, and we can, as we can for a spin 1/2, represent it on a Bloch sphere. So the north pole of the Bloch sphere, by convention, will be the circular state, and the south pole will be a low M state that we can reach by laser excitation. But I will always start from the circular state. So we are in the circular state, we set the resonant radio frequency field on, and what we observe is just a Rabi precession of the spin around the sphere. At any time, the spin is in a so-called spin coherent state that, for spins, plays the same role as being very classical as the current state of a harmonic oscillator. And if we stop at some time here, the spin coherent state is a superposition of various levels in the ladders with the proper coefficients. So this is the classical dynamics that we will base all our experiments on. So first, generation of a quantum Zeno dynamics. So first, what is a quantum Zeno dynamics? Jakob gave a very beautiful introduction to that on Tuesday, so I can go very fast on that. It's a generalization of the quantum Zeno effect. You all know, of course, of a quantum Zeno effect. You have a system, it's in an initial state, and it should have a current evolution, but we block the current evolution by very rapidly, very frequently measuring an observable of which the initial state is a non-degenerate eigenstate. This has been observed on ion traps a long time ago. This has been observed in cavity QED in a variety of settings. It is a well-known phenomenon, but of course, it gives much tellings about quantum measurement back action and things like that, but it's a bit boring because you always remain in the initial state. Quantum Zeno dynamics that has been put forth by our colleagues Saverio Pascasio and Paolo Facci, with whom we collaborate on that, leaves a bit more freedom to the system. Instead of measuring a non-degenerate observable, you measure an observable that has a degenerate eigenspace around the initial state. And what can be shown is that the system, the evolution takes place, but takes place only within that degenerate eigenspace. In other words, by asking repeatedly to the system a question, you can confine it in a subspace of the Hilbert space. And this confined dynamics can lead to extremely counterintuitive features. I should mention at this stage that there are three mathematically equivalent ways of generating the QZD, at least in the many interrogation limits. You can effectively perform the measurements. You can as well, and this is very much inspired by the bang-bang control, perform unitary kicks with the same eigenspace, or you can just continuously apply a state-selective perturbation which generates those unitaries. How can we enforce in the spin-state rotation, sorry, I've changed the labeling there, but it has little effect, in the spin-state ladder, how can we interrogate state specifically? We can just use a microwave transition to the adjacent multiplicities. Since the stark linear polarizabilities are proportional to the principal quantum number, all the frequencies of all the transition from one multiplicity to the next are non-degenerate, and we can individually interrogate that level in the multiplicity. So we perform the experiment, we set the interrogation on, we set the current evolution, the radio frequency rotation on, and later we probe the population of these various states by using also state-selective microwave probes. And from that, we can reconstruct or measure directly the evolution of the spin. The first row here presents you the evolution as a function of time of the Q function describing the spin. So if you are not familiar with spin Q functions, we are here close to the north pole of the sphere. The sphere is seen here in polar projection from the north pole. And since a sphere near the pole is nearly flat, we are very much in the same phase space as a harmonic oscillator. So this is basically the same Q function as that of a harmonic oscillator. So what happens? The evolution starts, and the spin starts moving. It's the rotation, the inhibited rotation. And at some point, it reaches the state we interrogate, that we can figure out like being a given latitude on the Bloch sphere. The lowest level latitude, the farther from the pole the state. So we move, and we reach this latitude. And if the quantum Zeno dynamics is correct, we cannot get through that latitude. So what happens next? The intuition would be it stops. But it cannot stop because the dynamic is still there. So it should move. But how to move in one direction without crossing the border? Quantum mechanics, as usual, has very fancy solutions to very non-trivial problems. Instead of going in that direction forever, the spin just, hop, reappears on the other side of the Bloch sphere and resumes its motion, and reappears, and resumes its motion. And it's that what you see here, at least the first oscillation. At that time here, the spin is indeed pointing in two opposite directions on the Bloch sphere, in two different directions on the Bloch sphere at once. Of course, this is a Q function representation. It doesn't tell much about the quantum nature of a superposition. It could be statistical as well. But in fact, by performing additional experiments, we have been able to determine the Wigner function of the spin at that inversion time. And you see this Wigner function is on the Bloch sphere, a beautiful blue planet with two continents that reveal the two directions in which the spin is pointing at once at that very given time. The continents are distorted. This is an effect of second-order Stark effect, basically. And in between, we have an archipelago of islands and depths, which are interference fringes, which reveal that this state is indeed a quantum superposition of states. So we do have at that time a real mesoscopic superposition of a large spin pointing at the same time in two different directions, admittedly, a kind of Schrödinger cat. I should mention that previous studies had been made in a low-dimension subspace, and this experiment has since been reproduced in circuit QED, and also, as mentioned by Jacob, on collective spins in an atomic ensemble. So this is, of course, a quantum game, and it could be an artificial quantum game, but think of these cats. What could we do with that? Think of the largest cat we could prepare in this case, which would be a superposition of North Pole and South Pole. This is the theoretical Wigner function. North Pole, South Pole, you cannot see it, and an archipelago of fringes on the equator. It's clear that if you rotate the Bloch sphere a small bit by 1/50th of a turn, you will turn even 100th of a turn, you will turn each island into a depth in the ocean. So you will completely change the state. In other words, these Schrödinger cat states are utterly sensitive to a rotation of a sphere. And what is a rotation of a sphere? It's just a change of the Stark frequency, just a change of electric field. So these should be very sensitive sensors of the electric field, and that drives me to the second experiment that appeared very recently on the 14th of July, unfortunately a badly remembered date this year, in Nature, and which was the subject of a poster by Eva Katarina Ditche, who, for this poster, as you know, received one of the gold keys yesterday night. So greetings. So we will try to make a quantum and Rydberg measurement of the electric field, something going beyond some quantum limit, some standard quantum limit. How can we, in this context, define the standard quantum limit? By performing an experiment with classical states, classical radio frequencies, basically by performing a Ramsey experiment with a large spin. So we start with a spin up. We flip it by a pi/2 radio frequency pulse on the equator of the Bloch sphere. It rotates at the Stark frequency. It accumulates a phase. And then we flip it back with a phase-tunable second pi/2 pulse. And the probability to return to the initial state has, of course, a maximum as a function of a phase of a second pulse. And measuring the position of this maximum gives you the rotation of the equator, and hence gives you the value of the electric field at the measurement time. This is just simple Ramsey experiment transposed to a spin 25 case. We have done the experiment, and you see here the circular state return probability as a function of the phase of the second pulse, and we do observe a maximum. It doesn't go all the way to 1, and it's a bit wider than the theoretical expectation that is there. This is due to the second-order Stark effect that makes the ladder of Stark levels slightly anharmonic. Nevertheless, it works, and that defines the standard quantum limit. The precision with which we can measure this phase is of the order of the phase uncertainty on the position of a spin, and the phase uncertainty on the position of a spin is well known to be in relative value 1 over square root j. Now, how can we do better? There is a much larger phase, which is here. It's the total phase that the spin, the total Berry phase, that the spin accumulates during its path on the Bloch sphere. Of course, for a spin 1/2, the two phases are the same, and it doesn't gain anything. But for a spin j, it is clear that the total phase acquired by the spin, because this sphere has a radius j, is j times larger. So there is a big gain in precision possible by measuring this total phase acquired by the spin on its path. But of course, this is a global phase. So if we had only one spin to play with, it would be no help, and there is no way to measure it. But of course, the spin, we took painstaking measures to isolate a spin here in the 50 manifold in the case of this experiment by using very cleanly polarized radio frequency, but we have all the other levels to play with. We have all the other manifolds to play with. Here comes the idea of the experiment. We will make a double Ramsey scheme. We will start in the 50 manifold spin up. And then with a microwave pulse, we will prepare a superposition of spin up in the 50 manifold and spin up, both circular state, in the 51 manifold. Due to the Stark frequencies being very different in both manifolds, the radio frequency that will manipulate the 50 spin will not do anything important to the 51 spin. So the 51 remains spectator, the 50 goes all its path along the Bloch sphere, returns near the initial state, we recombine, but of course the final recombination reveals a quantum interference that is sensitive to the global phase accumulated here. And if we think in between, we have a superposition of one circular state here, and one state, an elliptical state with a huge permanent dipole moment, which is, of course, another kind of a Schrödinger cat in this case. So what do we get? So this is the standard Ramsey experiment, just the 2 microwave pulse, for 2 slightly different fields. Fields differing by 566 microvolts per centimeter, admittedly a rather short amount. We barely distinguish the 2 curves, and of course we need a lot of stats to distinguish that. But if we go for the double Ramsey scheme, then we get inside this Gaussian envelope, we get interference fringes, which very clearly give a much better determination of the electric field. We gain a factor square root of j on the determination of the electric field. So of course, all that should be made a bit more quantitative. I define here the single-shot standard deviation of electric field measurement. This is a standard procedure in parameter estimation. If we repeat the experiment a large number of times, the imprecision that we get is like 1 over square root n. This is a trivial statistical factor, and I'm interested here in the single-shot, even though nobody performs single-shot measurement, in the single-shot estimation. It's plotted here as a function of the interrogation time, that is, of the phase accumulate on the equator. This is the standard quantum limit, the Ramsey experiment. This is the Heisenberg limit that we would reach with a North Pole, South Pole cat. And in between, we have our experimental points, which clearly go below the standard quantum limit for short interrogation times. For long interaction times, it diverges just because our experiment is so sensitive that most probably we see electrical noise on our electrodes. We didn't take too much precautions to screen the electrical noise, and this is just the reception of a radio broadcast in Paris, I think. What is interesting is, first, that we go with these quantum states below the standard quantum noise, but also that we achieve an interesting sensitivity, 1.2 millivolt per centimeter for 200 nanosecond integration time. If you put that, if we can get rid of these fluctuations, we could obtain a pi phase shift for the interference pattern for 200 microvolts per centimeter and a 1 microsecond interaction time. It means that with a couple of Rydberg atoms, we could be able to decide whether or not an electron, a single electron, is present at a 300 micrometer distance. This compares very well to the best electrometers so far. And in fact, the kind of vision we have is a sample of Rydberg atoms floating at a distance from some mesoscopic device, like a carbon nanotube quantum dot, and the Rydberg atoms being able, with a 1 microsecond bandwidth, to tell us whether or not we have an atom. And the recent progress that we made on cold Rydberg atoms on a chip is interesting in that direction. We also, this is a preliminary evidence of a North Pole, South Pole cat, but I have no time to discuss that. We also think of preparing superposition of two circular states with opposite magnetic momentum. An electron going in two opposite directions. It's interesting because it's totally insensitive to electric field, but of course allows for quantum-enabled measurement of a magnetic field. So it's time to finish up. I would like to mention that this is a teamwork. And the experiments I mentioned here are supervised by Sébastien Glaise, who is here in the room, performed by Eva Katarina Ditche, who is also here, Adrien Signol, who left us now, and Adrien Facon, who has also defended his thesis, PhD, and I would like to acknowledge a few funding sources. Thank you very much for your attention.
Thanks for sharing great work. We have questions.
Jean-Michel, my question may be more a semantic clarification about quantum Zeno effect. I've always learned that the quantum Zeno effect is a measurement, and the measurement broadens a level, and therefore the level is no longer populated. I think in your case, with a microwave, you have shifted a level. You haven't really broadened it. So in other words, you have put in a nonlinearity into an equidistant spectrum, which has exactly the same effect. But is it really a quantum Zeno effect?
That's a matter of terminology. And fuzzy, beautiful, shiny words are also extremely dangerous, are always extremely dangerous to manipulate. I would say that it's like non-alcoholic substitutes to beer. It has the same taste, it does exactly the same thing, it produces exactly the same taste, but of course the mechanism is slightly different. The mathematical equivalence of the various methods to generate a quantum xenodynamics, bang-bang control, measurement, or you are right that it basically sets a gap in a ladder of levels, has been shown mathematically in the limits of very many measurements. It's the differences, the imperfections of the quantum xenodynamics that are different for the three implementations. But what is important, in fact, is whatever you do, you interrogate a level strongly. You make a state-specific something, and you get this level out of the Hilbert space. And that blocks the evolution. That's the real thing about QZD. But, okay, semantics are difficult. I agree with you.
Okay, we'll have one more question.
Yes, the second order Stark effect breaks the degeneracy of the Stark ladder.
Yep.
How does that affect the experiment?
If I would like to discuss that in detail, first I should leave the scene to Sébastien or to Eva because it's very technical. Basically, there are many effects. The first effect is that the spin coherent state doesn't remain exactly a spin coherent state. It's just like if a current field state would propagate inside a nonlinear medium. It gets distorted. And this is the reason why we don't quite return exactly to the circular state at the end of the sequence. One of the reasons. Another thing is that the pulses that we apply have not infinite power. And so the rotation takes time. And the second order effect takes place during that rotation, which means that instead of having a beautiful straight trajectory on the Bloch sphere, we have something that is somewhat tilted. And if we don't have power, we cannot reach the South Pole. And one recent progress is that we have increased the power, so we can go now, in spite of the second order Stark effect, North Pole to South Pole directly. This is the signal I alluded to at the end of the talk.
Okay, thanks again. It's time to move on to the final speaker. So the next speaker is Carsten Klimt from Leibniz University, Hanover. So he'll talk about the EPL entanglement in a spinor Bose-Einstein condensates.